Euler's identity. What is it? Why did Richard Feynman, the famous physicist and Nobel Prize winner, call it the most remarkable formula in mathematics? That's a pretty strong phrase. Well, what are those crazy symbols, E, I, pi, and how can such strange, crazy numbers, which cannot even be written down exactly, equal such a simple thing as zero? Let's break this down by understanding what each of the symbols up there mean. Let's start with the easy ones. Zero. What is zero? We call zero the additive identity because if you add zero to anything, such as 1 plus 0 equals 1, you get itself, the answer. 1. What's that? Well, 1 is the multiplicative identity because if you multiply anything by 1, like 5 times 1 equals 5, you get itself. Again, the answer and what you're multiplying by 1 are identical. Next, let's tackle pi. Pi is the ratio of any circle's circumference and its diameter. Pi equals the circumference over the diameter. So if I stand on a circumference of a circle and start walking around the circumference, I will wind up traveling 3 diameters worth in distance, plus a little more, approximately 0.14 extra diameters. So that's why pi equals approximately 3.14. Okay, so that seems pretty straightforward. But what the heck is I? We call I the imaginary number. Oh boy, what does that mean? Numbers I can only imagine that aren't even real? Well, yes. How can that be? Let's start with a basic number line. I can add numbers to 0 and progress towards 1, 2, and so on. Or I can subtract numbers from 0 and go to the negative side of the number line. We know that. What if I multiply? Well, if I multiply positive numbers by a positive number, I just get a higher positive number. But what if I multiply by a negative number? Well, think of that as flipping to the other side of the number line. So if I'm at 2 and I multiply by negative 1, then suddenly that puts me at negative 2. I've flipped from the positive 2 to the negative 2. How about exponents? What does 2 to the second equals 4 mean? Remember that exponents are just multiplying the lower number by itself a number of times equal to the exponent. So 2 to the 2 equals 4 means 2 times 2 equals 4. And by the same principle, 2 to the third equals 8 means 2 times 2 times 2 equals 8. Good. But what if I want to know what x do I need in order to double it and get a negative answer? Or to put this in math terms, think of it as x squared equals negative 1. Okay, let's rewrite this as a more basic form. X times x equals negative 1. So that means we have to multiply something by itself and get back to negative 1. But if I try a positive number, it never flips to the negative side of the number. It only continues in the positive direction. And if I try a negative number, it will always flip twice and wind back up on the positive side. Oh no! What do I do? Now this is where the creativity in mathematics comes out. So far, we've only been thinking in terms of forward and backward or positive and negative on the number line. Let's break the rules a bit and say why not have a second dimension to our number line? Now some clever mathematician called the y-axis in this the imaginary axis, assuming that our old friend the number line on the x-axis is the real axis. But let's not worry about that. Let's just say we have a two-dimensional line called the complex plane. Okay, so now what is I? We can now break out of the real number line and move in the complex plane. If I'm standing at 1 and I multiply myself by I, let's say that means I rotate myself by 90 degrees, counterclockwise. So okay, now I'm at x equals 0 and y equals I. Cool, now I multiply myself again by I and rotate myself another 90 degrees. Where am I? Now I'm at x equals negative 1 and y equals 0. Back on the real number line. Awesome! I can flip to the negative part of the number line by simply rotating myself twice around the complex plane. Now, in other words, to my earlier question, what x is x squared equals negative 1, or x times x equals negative 1? To answer this, x equals I, or in other words, I times itself equals negative 1. One concept left, Euler's number, or E. What is Euler's number? Before we get into that, let's go to the bank. Let's imagine we had $1 in a bank, and every year it doubled. So year 1, we have $1. Year 2, we have $2. Year 3, we have $4, and year 4, we have 8, and so on, twice as much every year as the year before. Using a math notation, we would denote this as 2 to the x equals m, where x is the number of years we earn interest, and m is the amount of money we have at the end. Now that sounds like a lot of money, right? Every year it doubles, but can we do better? Suppose now the bank gives you 2 offers. It will double your money every year at the end of the year, or pay you half your money twice a year. Well, you'd be tempted to choose the double every year option, or think that they're at least the same. But let's think this through. Here's how much money I make after 1 year in the first option. But if I get paid half my money in the half period and other half at the end, I will still end up with the full amount I'm due at the end of the period. Except, and this is exciting for our ability to make more money, in the second example, I also get paid interest on the first bit of money I got. Wow, that second option makes me richer. I want that one. Okay, but what if the bank agrees to pay me interest 3 times per period instead of twice? Look at that. I made even more money. I like this more frequent adding of interest, but as the compounding period becomes shorter and shorter, the amount of money I can gain only increases so much. Eventually, it flattens out as interest payments become very, very short, almost instantaneous. Now would be a good time to take another look at the formal definition of Euler's number. Whoa, hang on, more symbols. Don't worry about it. This just says that as we compound our money with a shorter and shorter time frame until we hit continuous compounding. Do you remember that 2 in our earlier equation? 2 to the x equals m. This 2 becomes E, or Euler's number. E to the x equals m. Euler's number approximates about 2.718. So, now we know that whenever we compound or grow a value continuously, we use Euler's number raised to a certain power. Now let's bring everything back together and take a look at Euler's identity again. We know what each part means on its own. How can we combine our knowledge to make sense of this thing? Okay. Pi relates to circles and the ratio of circumference to diameter. I is the imaginary unit and deals with rotation into the complex plane. And raising e to the power of something represents a continuous and instantaneous compounding for a certain length of time. Okay, so let's read Euler's identity with words and ideas, not math. Imagine that each of these symbols are superheroes, using their own special power, but helping each other and acting together. So we start at 1 on the number line, on the circumference of the unit circle, and now we start moving. We start adding up tiny, tiny segments of length continuously, so we need our superhero E, the continuously compounding superhero. But we want to rotate in the complex plane. So that's fine. We need I, our complex rotation superhero, pulling us in the complex direction. Now how far should we go? Let's go pi distance, which is halfway along the circumference of a unit circle. Thanks, superhero pi. Where did we wind up? Holy cow, we're at -1. Now if we just add up 1 along the real number line, we finish our journey at 0. So why is Euler's identity considered beautiful? Why is it the most remarkable formula in mathematics? Why are we so in awe of its deep insight? Well, first of all, I don't know about you, but I think it's just beautiful to look at. Take a look at it again. But also, it's amazing because it pulls together these very, very different things that seem apparently unrelated. Continuous compounding interest, the complex number plane, and circles, and shows us a surprising relationship which is extremely simple. Just add 1 to e to the I pi, and you end up with nothing. Wow, such a deep insight, right? Well, now you know a little more about the beauty in math.